Sound check 1. Sound check 2. Okay, good morning everybody. Let's go ahead and get started. We're going to talk about section 9.3, the geometry of triangles, but you can always post any questions in the chat box. Okay, so for section 9.3, we're going to talk about congruent triangles, similar triangles, the Pythagorean Theorem, which relates the lengths of the sides of right triangles, and we're going to work some, there is going to be a little bit of calculation involved, not just definitions this time. So, triangles that are both the same size and the same shape, so same size and the same shape, are called congruent triangles. Same size would mean that the lengths of their sides are the same. Same shape would mean that their angles are the same. In order to indicate that the corresponding sides have the same length, you see how we mark these little marks on here. So this would indicate that the side DE is the same length as the side AB. And the way that we indicate congruence is with this symbol. It looks like an equal sign, but with a little tilde over it. So that means that the two triangles are congruent, same size and same shape, but the order of the letters and how you name the triangles is going to matter. So again, we saw that AB is the same length as DE, and you'll notice that when we name the triangle ABC and say it's congruent to DEF, the AB and the DE are the first two letters in each, right? So without looking at the diagram, I could also tell you that BC must be the same length as EF. And we can confirm that here. CEF has 2 marks and BC has 2 marks. And then finally, the ones on the end, A and C, D and F, we know that AC and DF must be equal. So the position of the letters in the statement triangle ABC is congruent to triangle DEF is important. It not only gives you the relationship between the lengths of the sides, but also the angles. So angle A, for example, is the same as angle D, same measure. And you can see that here because there's one mark on angle A and one mark on angle D. Angle B is the same measure as angle E, and you can see that because each of these has 3 marks. So they're the same measure. And then angle C is the same as angle F, and you can see they each have 2 marks up here. So this statement communicates a lot about the relationship between the triangles. Now, we would like to know what's the minimum amount of information we would need in order to guarantee that 2 triangles are actually congruent. There are several ways that this can happen. One of them is called side angle side, and that says that if 2 sides and the angle between them are equal in measure, then the triangles are congruent. Let me draw a picture of that. So let's say that we had our triangle ABC and our triangle DEF, and they look like they're congruent, but we need to be able to prove it for sure. It would be enough to know that for the length of side AB is 6 and the length of side DE is 6. The length of side AC is 10 and the length of side DF is 10. And the measure of this angle in between, angle A and angle D, are both 30 degrees. So if we know that 2 sides and the angle between them are the same, that guarantees the rest of the measures have to be the same as well. So that's how we use side angle side, which is abbreviated SAS. Another way that you can determine that 2 triangles are congruent would be that you're going to look for the relationship that 2 angles and the side in between them are equal. So again, let me draw a picture here. If we have triangle ABC and we have triangle DEF, how do we know that they're actually the same size and shape? Well, one way would be if suppose somebody told us that angle C is 30 degrees, angle F is 30 degrees, angle B is maybe 90 degrees, and angle E is 90 degrees. And then the side in between, BC and EF, those sides are both length 7. Then we would know by angle side angle that we have the rest of the dimensions must be the same as well. And then finally, if all 3 sides are the same lengths, then they also have to be congruent. So maybe we have a triangle with side lengths 5, 6, and 7, and another triangle. And by the way, let me draw this triangle slightly differently, because sometimes when we're analyzing the triangles, they won't line up very nicely. So even if this triangle is backwards from the other one, as long as you know that all 3 sides have the same length, then we know that these are in fact congruent triangles. Let me label them A, B, C, and D, E, F. Alright, so what we see is that side EF is the same as AB, and side ED is the same as BC, and DF is the same as AC. So how could we write that in symbols so that ABC is congruent to the triangle what? How would that have to line up? So you can tell because angle A is between 5 and 6 that it has to match up with angle F, and B is between 5 and 7, so that matches up with E. E is also between lengths 5 and 7. And then the last one, C, has to match up with D. So knowing 3 sides of a triangle are equal guarantees that they're congruent as well. Another important set of facts that you might be asked to kind of keep in the back of your mind and answer questions about has to do with isosceles triangles. Remember, isosceles triangles are triangles where 2 sides are equal. In this case, we're told if triangle ABC is an isosceles triangle with AB equal to CB, so these are the 2 equal sides, and if D happens to be the midpoint of the base AC, so D is halfway between A and C, in other words, then the following properties hold. First of all, the base angles A and C have to be equal to each other. So for item 1, what that's saying is that angle A must be the same as angle C. Also, angles ABD and CBD are equal. So let's see what that looks like. ABD, we need a line segment to visualize that. So let's go ahead and connect here. Okay, so angle ABD is referring to this angle here, and CBD is referring to this angle here. These 2 have to be the same as well. Oops. So that's item number 2. And then ADB and CDB are both right angles. So ADB is referring to this angle here, and CDB is referring to this angle here. All right, so essentially what we see is that every isosceles triangle is actually a pair of right triangles. More than that, a pair of congruent right triangles. And you can see that they're congruent because we have angle, side, angle, right? Angle A and C match up. The side between A and B matches up with the side between C and B. And then the angle ABD matches the angle CBD. So those are 3 conditions that you need to be aware of. So if you're given an isosceles triangle, you can use those facts to draw conclusions. All right, we're also going to talk about working with similar triangles. Similar is a less stringent condition. Similar just means they're the same shape, but not necessarily the same size. So in order to be considered similar triangles, all of the angles have to be the same, right? That's what same shape means. But the sides aren't the same length necessarily. But we can say that the ratios of corresponding sides must be constant. The corresponding sides are proportional, in other words. What does that mean? Well, maybe one triangle is exactly twice the size of the other in lengths. So for example, maybe I have a triangle that has lengths 6, 5, and 4, and then I have another triangle, and if I know that these 2 triangles are similar, then the lengths of these sides must be multiples of those. Let's say it's twice as big. This would be 8, 10, and 12. Or maybe it's 1.5 times as big. So 1.5 times 4 would be 4 plus half of 4, so 6. 1.5 times 5 would be 5 plus half of 5, so 7.5. And 1.5 of 6 would be 9. 6 plus 3. So these would be considered similar triangles because they're the same shape, but they're not the same size. But given any pair of sides from one triangle to the other, that will tell you what the proportion is going to be. So how do we know if two triangles are similar? What's the minimum amount of information we would need? So angle is how you would know. If the measures of two angles of one triangle are equal to those two of the other triangle, then the two triangles are similar. All right, so let's take a look at how we might use the similarity properties. So triangle ABC, we're told here on the right, is similar to triangle DEF. So by the order of the is the same measure as angle D. Okay, and angle B is in the middle, and so is angle E. So we know angle B is the same as angle E. And then angle F and angle C are the same. Now, this is a common type of problem. They will give you the lengths of the sides of one of the triangles and only give you one of the lengths of the sides of the other triangle. And what they want you to do is use the fact that the proportion is constant. So in other words, for example, if we make a ratio of the length of the side BC over the length of the side EF, that has to be the same proportion as if we took the length of the side AC over the length of the side FD. All right, so which out of these lengths, we know several, right? BC is 16 and EF is 8 and AC is 32 and FD we don't know. All right, but notice that 16, well, I'm going to show you two ways to solve it. Notice that this is a ratio equal to 2. 16 divided by 8 is 2. So that means that the bigger triangle is twice as big as the smaller. So 32 is the bigger, so if we divide it by 2, we get 16. That must be the length of the side of the smaller triangle. Okay, you can also set up an equation. 16 over 8 equals 32 over x. If you want to, you can reduce this to 2 over 1, or you can leave it the same. I like to reduce because that gives me smaller numbers to work with. And then there's a little trick for solving. This type of equation where you have one fraction on each side is called a proportion. And you can solve a proportion by doing what's called cross multiplying. The product of the means equals the product of the extremes. So 2 times x has to be equal to 32 times 1. So if 2x equals 32, divide both sides by 2, and we get x equals 16. All right, so this is a procedure that you can use in order to solve for a missing side of a triangle. So we have established this side is 16, DF, or FD, however you want to call it. All right, now you can probably tell just looking at these two triangles what the length of side ED is, right? Because ED is going to be half as big as AB, so that AB is 24, so this is just going to be 12. But let's go ahead and set up a proportion to show how we might get that using algebra. So let's suppose we didn't figure out that that has to be half of 24. We can set up any proportion, any pairs of sides that we want, and they have to be equal. So for example, we might compare 8 to 16 here and here. and then that would be x to 24. It would be the same ratio as x to 24. Okay, if you want, you can reduce the left side to 1/2. And then we're going to set up our proportion. We're going to do our cross multiplication. And so we're going to have 2x equals 24. Divide both sides by 2, and we get x equals 12. So we come to the same conclusion that way. Now sometimes a triangle won't be a nice even multiple of the other ones, so setting up this proportion is really helpful because it's hard to do it in your head. Okay, another fact about triangles that we're going to be using is the Pythagorean Theorem. Most people remember the Pythagorean Theorem. It says that if you label the sides of a right triangle, this particular one only works with right triangles. If you label the sides A, B, and C, where C is the hypotenuse, which is the side opposite the right angle, then the relationship between the sides is always a squared plus b squared equals c squared. And it's called the Pythagorean Theorem because they give credit to Pythagoras for figuring this out. There's a nice little link where you can go and see why this is true. But we're just going to work with it. So we're going to look at some examples, some of which are talking about using the Pythagorean Theorem, and some of them require knowledge of similar triangles. I find that, look. Alright, so here we have a MyMathLab example where it says there are two similar triangles in the diagram. So in this case, they're telling you you're using similar triangles. That's a clue. Find the unknown measurement. Alright, so, oh, are you losing the, are we breaking up? I see somebody posted a comment that the feed is breaking up. Tanya said it is. Is anyone else having that trouble? I'm sorry to hear that. Let me see what's going on here. Alright, my internet access looks a little slow, but I'm not seeing Sorry guys, I'm not seeing anything I can do to fix that at the moment. Alright, well, if I need to repeat anything, just let me know. I'm going to keep going. So in this diagram, it says there are two similar triangles. So let's figure out where we see those two similar triangles. So similar, remember, means the same size, the same shape, but not necessarily the same size. So I see two triangles in this diagram, and I think when the two triangles are drawn together like this, it's really a good idea to draw them separately. So that's what I'm going to do. Alright, so the bigger triangle is ROS, and the smaller triangle is POQ. And there, let's see, let's put what dimensions we know. So RS is 90. OR is the sum of 60 and 120, so that's going to be 180. And then OP is going to be 60. And X is what we're looking for, which is PQ. All right, since we were told they are similar triangles, and I know angle O is the same as angle O, all right? Then it must be that triangle ORS is congruent to OPQ. And the way we write that is ORS triangle is similar to, same shape as OPQ. All right, we can set up proportions. So we're going to set up, for example, we know that 180 is proportionate to 60 as 90 relates to X. I have the larger triangle on the tops and the corresponding sides of the smaller triangle on the bottoms of the fractions. All right, so this comes from the larger triangle, as does this. And these two are corresponding sides of the smaller triangle. Uh-oh, what's oh no? I'm just checking again to see if we have internet. Let's see. Oh, okay. Good idea. Did refreshing the page work? Oh, good. Okay. So, to solve a proportion, we're going to multiply this way. But before we do, let's reduce a little bit. I noticed that they're both divisible by 10, so that gives us 18 over 6, but 18 over 6 is the same as 3 over 1. So I'm going to multiply 3 times x and 1 times 90, so I get 3x equals 90. So now dividing both sides by 3, we get that x is equal to 30. Now, you might have known that already because, look, you might have observed, well, 60 is a third the size of 180, so a third the size of 90 must be 30. And you can do it that way mentally, or you can set up the proportion. Any questions about this one before I move on? Okay, there is a bit of a lag time, so, you know, it's okay to ask your question and then I can come back to it. Let me see here. Okay, another type of question would be something like this. If the hypotenuse of a right triangle is 1 meter more than the longer leg and the shorter leg is 5 meters long, find the length of the longer leg. All right, so when they tell you that you have a right triangle, and they're talking about, so we mentioned a right triangle. This is a clue phrase, right triangle. And they're talking about the lengths of the sides. Then that's an indication that we're going to be using the Pythagorean theorem. In this case, they did not give us a picture. So as soon as you read that it's a right triangle, draw a picture. It doesn't matter if your triangle is exactly, you know, the shape that it's going to turn out that these lengths need to be. Just something to give you a frame of reference for where we have the legs. The legs are the sides touching the right angle, and where we have the hypotenuse, which is the side opposite the right angle. Normally we refer to these as A, B, and C when we're talking about a right triangle. Okay, so it says the hypotenuse of the right triangle is 1 meter more than the longer leg. So if we're comparing the hypotenuse to the longer leg, then let's say that the longer leg is x length. Then if the hypotenuse is 1 meter more than x, then it would have to be x plus 1. And let me do this in a different color so it's easier to see. Okay, so if this is side x, this side would be x plus 1. And then the shorter leg is 5 meters long, period. So we can just label that 5. Find the length of the longer leg. Okay, so we're going to set up the equation, the relationship a squared plus b squared equals c squared. And then side A was 5 units long, so we have 5 squared. Side B was x units long, so that's x squared. And then side C is x plus 1 units long, so that's x plus 1 squared. Okay, so this equation is a little bit more advanced than the linear equations we looked at in the last section, but don't worry, it works out neatly. So what I mean is, think of this x plus 1 as x plus 1 times x plus 1, and we're going to FOIL. Do you remember when you multiply two binomials together, you can use FOIL, first times first, outer times outer, inner times inner, and last times last. FOIL. All right, so what are we going to get here? We're going to get 25 plus x squared equals, first times first would be x squared, outer times outer would be x, inner times inner would be 1 times x is x also. And then 1 times 1 is 1. So we have the equation 25 plus x squared equals x squared plus 2x plus 1 if we combine like terms. Now notice that there's an x squared on each side, and then in an equation it stays balanced if we remove the same amount from both sides. So I'm going to subtract x squared from both sides to get those to cancel out. So we're left with 25 equals 2x plus 1. And this looks more like the type of equation that we've been seeing, the linear equations. I believe that in your MyMathLab homework, I've removed any questions where the x squared doesn't cancel out, because that would result in solving a quadratic equation, and I don't want you to have to do that. So if you find that those have been left in, please let me know and I'll fix it. So I only want you to solve the problems where the x squareds cancel out. All right, so in this case then, now that we're down to just an x and no x squared, we can just get the numbers on one side and the variables on the other. So subtracting 1, we get 24 equals 2x, which means that x is equal to 12. All right, now we're supposed to find the length of the longer leg, and that's exactly what x represents. The length of the longer leg is 12. 12 meters in this case. All right, any question about that problem? Okay, so if you have any questions, just post them on the chat box and I'll come back to it. Okay, let's take a look at this example here. How high is a tree that's supposed to say casts a 33-foot shadow at the same time a 7-foot post casts a shadow which is 12 feet long? All right, so whenever you see casts a shadow, this is an indication that you're going to be using similar triangles, and I'll explain why. So let me draw my little tree here. Here's my little tree. Okay, the sun is up here somewhere. And when it shines on the tree, it creates a shadow on the ground. Okay, so here's the shadow of the tree. And the length of that shadow is determined by the angle at which the sun is hitting the tree, right? So if on the same day, at the same time, we have a lamppost. Let's say this is my lamppost here. All right, so here's my lamppost, and the sun is going to be hitting it at the same angle, and it's going to create a shadow for this guy over here. All right, so the tree has cast a 33-foot shadow. Oh, I got to go back because we have a question about the previous problem. Hold on a sec. All right, so the question was, where did the 2x come from if we cancel all the x's in the equation? So the 2x comes from, we didn't cancel all the x's, we just subtracted the x squareds from both sides, which makes them cancel out and become 0. The 2x came from when we FOILed out this expression over here, x plus 1 times x plus 1. First times first is x times x, which is x squared. Outer times outer is x times 1, which is x. Inner times inner is 1 times x, which is x. And last times last is 1 times 1, which is 1. So it gives you x squared plus x plus 1. Now remember, 1x and 1x adds up to 2x. So that's where the 2x came from over here. Okay, so it was x squared plus 2x plus 1, but then I subtracted x squared from both sides. So let me write the equation up at the top here. We had 25 plus x squared equals x squared plus 2x plus 1. So what I was saying is x squared and x squared are like terms. In fact, they're identical terms. So if you subtract from both sides 1x squared, those are going to cancel out, which leaves you with 25 equals 2x plus 1. Okay. Back to the other problem. All right, so we have our tree casting a 33-foot shadow, and our lamppost, I think it was, casts a 7-foot shadow at the same time. Now, the tree is roughly at a right angle to the ground, as is the post. So, oh, not a 7-foot shadow, I'm sorry. That was a 12-foot shadow coming from a 7-foot post. Okay, sorry about that. All right, now they're both right angles, and the sun is striking them at the same angle. And by the way, since all triangles add up to 180, this third angle must also be the same. Remember, you only need 2 angles, angle-angle property, in order to get all 3 of the angles to be the same, so that we have similar triangles. So we can set up a proportion. We are looking for the height of the tree, so I'm going to call that x. So we're going to say that x from the larger triangle is proportionate to 7 from the smaller triangle, but also 33 from the larger triangle is proportionate to 12 from the smaller. So we've set up a proportion, and we can cross multiply. Okay, so let's see, 12 times x is 12x, and then we have 7 times 33. Let's see, what's 7 times 33? That's going to be 210 plus 21 is 231. Check my arithmetic for me, guys. So 12x equals 231. And then we're going to divide both sides by 12. And let's see what that turns out to be. Pull out our handy dandy calculator here. All right, so we have 231 divided by 12. And we get 19.25. Okay, so x is equal to 19.25 feet in this case. Alright, so that's the end of that one. Again, I just want to point out that when you see the cast a shadow thing, that usually means it's similar triangles. So start trying to set up a diagram where you have, you can compare the proportions. Okay. Here's another type of problem that involves the Pythagorean theorem. It says if positive integers are chosen for r and s with r greater than s, then the following, it should say, set of equations generates a Pythagorean triple. So all this is a formula where you can find what's called a Pythagorean triple. And what is a Pythagorean triple? Well, there are only certain sets of numbers that would satisfy the equation a squared plus b squared equals c squared. Just as an example, 3, 4, and 5 happens to be a Pythagorean triple because notice that 3 squared is 9, 4 squared is 16, and 5 squared is 25. So 9 plus 16 does equal 25. So 3, 4, 5 would be an example of a Pythagorean triple. In other words, there are right triangles that have those dimensions. Okay, so people wondered, like, how can I get more triangles that have that are right triangles? What dimensions would they have to be? to satisfy a squared plus b squared equals c squared. And they came up with some ways to do that. And this is just one of the patterns where if you plug into it, you'll always get a Pythagorean triple. Okay, so let's go ahead and try it out and just see that it does work. All right, they're telling us to use the values r equals 7 and s equals 1 together with these formulas to generate the Pythagorean triple. So if r is 7 and s is 1, then let's find a. A is always r squared minus s squared. So in this case, a would be 7 squared minus 1 squared. That's going to be 49 minus 1, which is 48. Okay, now let's see what value of b goes with that. So b is always equal to 2 times r times s. So plugging in 7 and 1 again, we have 2 times 7 times 1. So b would be 14. And then c is supposed to be r squared plus s squared. So that would be, well, let me write out that, r squared plus s squared. So c would be equal to 7 squared plus 1 squared, which is going to be 49 plus 1, which would be 50. All right, so supposedly, if you have a 48, b 14, and c 50, this is a Pythagorean triple. There's a right triangle that has those proportions. And let's go ahead and check by plugging into a squared plus b squared equals c squared. So 48 squared plus 14 squared is supposed to equal 50 squared. Let's see if that works. So getting out my calculator. And I do want to remind everybody that when you take your midterm, you are going to need to bring a calculator, and you cannot use your cell phone as a calculator. So 48 squared is 2304. And let's write that down. 2304 plus, now let's find 14 squared. That's 196. And that's supposed to equal 50 squared, which would be 2500. And it does, right? 2304 plus 196 is 2500. So it does satisfy a squared plus b squared equals c squared. So when you see these questions in MyMathLab about generating Pythagorean triples, it's really not, it's just asking you to plug in and into the formulas. You don't even have to do the last part that I did to demonstrate that, this part here where I demonstrated that it actually satisfies the Pythagorean theorem. You don't even have to do that. This is just to check. It would be a way of checking. But the answer would just be 48, 14, and 50. Okay, now remember when we studied logic, we learned that if you have the conditional statement if P then Q, then the converse of that was if Q then P. So I want to talk about the converse of the Pythagorean theorem. So the Pythagorean theorem says that if you know the sides of a right triangle are A, B, and C, then a squared plus b squared has to equal c squared. So that's an if-then. if A, B, and C are sides of a right triangle, then A squared plus B squared is equal to C squared. What this is talking about is the converse. If you have the sides of a right triangle, A squared, and it turns out that A squared plus B squared is equal to C squared, then that guarantees that the triangle is a right triangle. Right, so you might not know the original triangle is a right triangle, but if you observe that the relationship between the lengths of the sides satisfies A squared plus B squared equals C squared, then you can conclude it's a right triangle. And in fact, you'll know that since C is the longest side opposite the right angle, you'll be able to identify which angle is the right angle. So for example, if I gave you a 3, 4, 5 triangle, we already talked about the fact that 3 squared plus 4 squared equals 5 squared. So even if I don't tell you the measure of any of the angles, you would know that the angle opposite the longest side must be a right angle. So the converse of the Pythagorean theorem is significant as well. I could ask you, is a triangle with sides of length 4, 7, and 8 a right triangle? And you could check that, because you could say, well, does 4 squared plus 7 squared equal 8 squared? Well, that would mean that 16 plus 49 equals 64, but it doesn't. 16 plus 49 equals 65, right? So, no, that's not true. So that means that this is not a right triangle. Okay, so that's all for today. If you have any questions about anything we talked about, you can always email them to me, or any other questions, of course. So also, if you could give the video a thumbs up, that helps other students to find the video. I'd appreciate that. And throughout the week, you can always send me your Ask My Instructor questions. So you guys have a good day, and I'll see you in class next week if I don't talk to you between now and then. Bye-bye.